Welcome everyone to another lecture. Today, we'll be going over something that is Introduction to Electromagnetism. This is a very important topic. So I would really appreciate your patience to go throughout the entire lecture. So I am Kushal Gurbet, and I'll be explaining this topic to you today. I will be starting my slide with a very great quote by Richard Feynman that says, "A physical understanding is a completely unmathematical, imprecise, and inexact thing, but absolutely necessary for a physicist." So, why study electromagnetism? Well, the Maxwell's equations explain a diverse range of phenomena, from why a compass needle points towards north or south to why a car starts when you turn the ignition key. They are the basis for the functioning of such electromagnetic devices such as electric motors, say cyclotrons, TV transmitters, receivers, telephones, fax machines, radar, and microwave ovens. So cyclotrons it is. So as you can see, this is the magnetic field and that is produced by the moving of this electric charge. This is the direction of the propagation of that one unit of electric charge. So next slide, we'll proceed to the next slide now. Um, Okay, so this is Maxwell's equation. So for Gauss, for our E here, this has integral of E times dA, that's Q over ellipse naught. It says that how charges produce electric fields. The field lines begin and end on a charge. Then we have Gauss for vector B, that's given to us as vector B, d integral of vector B dA. No magnetic charge, magnetic field lines don't begin or end here. Then we have Faraday's law. That is Faraday's law that is given to us as the integral of E vector times dr. That's simply as d phi b by dt. It tells us how the changing magnetic flux produces electrical field. After that, we have our unit ampere, Ampere's law. So that integral of this u vector b times dr gives us nu naught I plus nu naught ellipse naught d phi e and dt. So the electric current and changing electric flux produce magnetic field. That's what Ampere's law says. Our aim is to understand these equations, not necessarily remember them. That's why I have written the laws over here as well. So there are some, you can just take these extra online resources for quizzes. Okay, so in this lecture, you will learn how matter and many of its interactions are fundamentally electrical, about electric charges as a fundamental property of matter, to describe the electric force between charge. Okay, so by the end, we will learn about the electric field, how to calculate the fields of discrete and continuous charge distributions, how charges respond to electric fields. So we know that same signs repel, opposite signs attract. The Coulomb's law quantifies the force drawn compare with gravity. Okay, now we'll go with the electric charge, force, and field. So one of these, so as you can see, just a second. So insulators can be charged. Charged objects can attract neutral objects. Neutral does not mean no charges. Charge is not an object; it is a property of matter. There is no fundamental reason why electrons have to be negative. There is no difference between a charge and a current. Um, just a second. So the answer is F. The current is motion of a charge. There's no difference between charge and current. So the false statement out of them is that there is no difference between charge and current. The answer to current is the motion of charge. An A and B example, that balloon sticks to wall, that gives us example that static charges can be produced in insulators. And for B, that charged objects attract neutral objects. Next is charge conservation. A charge is transferred, never created nor destroyed. Here the charge quantization, it's given to us as E, that's 1.602177 times 10 to the power 19 C. That's approximately equal to 1.60 times 10 to the power 19 C. Now this is our exercise. Okay, it's hard to understand. Wait. The answer for this is the two unions of positive charge, the two spheres will be bottom attached. What is the final charge of each sphere? Explain. So answer one, the final charge. So each sphere ends up with one unit of negative charge. Once it touches the sphere, becomes essentially one conductor. The overall net charge is -4 plus 2, that equals to -2. The charge is spread uniformly over the surface of a conductor. Conductors and insulators. In materials such as wood or glass, all the electrons are bound to nearby atoms and none can move freely. These materials are called insulators. In many materials, such as copper and other metals, some of the electrons are free to move about the entire material. Such materials are called conductors. Charge by induction. Conductors in contact become oppositely charged when a charged rod attracts electrons to the left spare. If the spares are separated before the rod is removed, they will retain their equal and opposite charges. When the rod is removed and the spares are far apart, the distribution of the charge of each spare approaches uniformity. So, exercise 2. Two identical conducting spares, one with an initial charge of positive Q, the other initially uncharged, are brought in contact. What is the new charge? A plus Q or B? Half of Q. Okay, you need to solve for that. So, answer is half of Q. Since the spares are identical, they must share the total charge equally. We have just learned over here. Next is, while the spares are in contact, a negatively charged rod is moved close to one spare, causing it to have a charge of plus 2q. What is the charge of the other spare? Think for it and then answer the answer. One, two, three. You have the answer yet? I suppose it's a very easy question. So, so minus q is necessary to satisfy the conversation of the charge. Okay, now Coulomb's law. Charles Coulomb, 1736, was born 1736 and died 1806, studied the force exerted by one charge on another using a torsion balance of his own invention. So here's this torsion fiber, and there's this charge with balls in the scale. So this is our exercise. So for each pair of charges, draw a vector on each charge showing the electric force acting on that given charge. The length of each vector should be proportional to the magnitude of the force. Each plus and minus symbol represents the quantity of charge. Okay, so here A, what is the value of A? Let's look at. So equal and opposite charges forces. The force exerted by one point of charge on another acts along the line between the charges. It varies inversely as the square of the distance separating the charge and is proportional to the product of charges. The force is repulsive if the charges have the same sign and attract if the chain charges have opposite signs. So here, the magnitude and direction of the electric force exerted by the charge Q1 on another charge Q2, a distance r away is given as F12, F12 vector, that's Coulomb's law given to us as KQ1 Q2 by R square R cap. Here, K is an experimentally determined constant. The value of K, 9.0 into 10 to the power 9 Newton meter squared, C squared. C stands for the speed of light. So this is our notation for Coulomb's law. And this is our unit vector r cap. Diagram needed. Okay, the unit vector r always points away from q1. Here the product q1 q2 is positive, so f12 is in the direction as the same direction of r cap. So as you can see this Coulomb's law, the q1 and q2, the unit vector r between them is in the same direction as r. So this r cap and the f12, the Coulomb's law, both stand in the same direction. So this is the source charge, and this is our field charge. Q1 is the source charge, and Q2 is the field charge. Unit vector r always points away from q1. So this r cap always points away from our original source charge. So this always points away from the source charge. The field charge is now negative. Here the charges have opposite signs. So q1, q2 is lesser than 0 and f12 points opposite r cap. So r cap is in this direction and f12, the Coulomb's law, is in that direction. Okay. So example, this is our next problem. So finding the wait a second. It's slide position. So we need to find the remaining two charges. At 1.0 Newton C charge, new C charge is at equals 1.0 centimeters, and minus 1.5 new C charge is at x equals 3.0 centimeters. What force does the positive charge exert on the negative one? So read the problem solving strategy for using Coulomb's law here. So we will be evaluating it. So draw, this is your homework for today if you need to be solving this question. Okay, using Coulomb's law, remember the force is a vector. If assess if the force is in the direction you expect for the sign of charges. So we approach the end of our lecture. Okay, so thank you for watching. Hope you subscribe and do this problem. And if you get the answer, kindly comment it below. That means that you understood the lecture very well. So thank you for watching. Goodbye.